Okay, so for today's little exercise, I think we do throw back to good old-fashioned kinematics. Let's look at a quick one. Let's say that we have two jets of water or some liquid that's being launched from a hose. So here at the origin, I've put my hose. We're launching these jets at two different angles. I'll call them angle alpha with the horizontal and angle beta with the horizontal, but crucially, they're being launched at the same initial launch speed. And the question is, only given that information, can we figure out how far away they will intersect, these two jets of water. Now, presumably we would do this at kind of two different times, but let's pretend we've got identical hoses or something that are angled at these two different angles, and I want to know what is the horizontal location of their intersection point. Okay, so let's go ahead and start with our trajectory equation. Remember that this was derived under the assumption that the gravitational field is uniform. We're ignoring drag. We're setting our launch point here at the origin. And then I'm going to leave this launch angle theta completely generic. We'll go in sub alpha and beta in just a sec. But this is sort of our starting point. Now what I want to do is recognize that when these two jets cross, they'll of course have the same x position and y position. So I can just write down two copies of this equation with the same value of y and set them equal to each other. The only difference will be that we have two different values for theta here. I am going to go ahead also and rewrite this cosine squared as a secant squared, and we'll see why that can be pretty useful. So let's go ahead and get those on the board. Whew, just barely made it. Okay, so here we have our two y coordinates set equal to each other. We've got the two different values for theta, so alpha on the left and beta on the right. And what we want to do now is try to simplify this as much as possible. So what I'm going to do is recognize that there is an x in every single one of these terms. Of course, we can cancel those out because, well, yes, there is an intersection point at x equals 0, but that's not very interesting. So we'll go ahead and cancel one x from every term. Let's also remember that x is actually the thing we're trying to solve for here, so it's kind of nice. And then I'll go ahead and move these two tangent terms to the left and the two secant terms to the right. Let's see what happens when we do that. Okay, so this isn't looking so bad. We want to solve for this x, and it looks like we're pretty much done. But we can do one last little bit of trickery here, which is to use our Pythagorean identity for tangent and secant. So recall, I'll just sort of write it down below here, that secant squared of an angle is 1 plus tangent squared of that angle. And if we use that relation here for these two secants, I'm going to get a 1 plus tan squared alpha minus 1 plus tan squared beta. The ones will cancel, and I'll just end up with a difference of tangents. Now that looks pretty nice because it's a difference of squares, and we know how to factor that pretty nicely. So let's go ahead and write that as a difference of tangents, and then solve for the x by itself. So what we'll have here, of course, is 2v0 squared over g. That's the only thing that's got units of distance anyway, so we're not surprised that showed up. And then we'll have this difference over the difference of tangents squared. Okay, now, as promised, this nicely factors into, well, a difference of squares. So we'll have a tangent minus tangent. That's going to cancel with this top bit. And then we'll have a tangent plus tangent left over. And that does give us our final answer, which is a nice compact form. Depends only on the given parameters. We can see there's sort of a dimensionful quantity here. V0 squared over g is the only way you can get distance out of the given bits, so we're not surprised that shows up. And if we wanted to, we could also check some things like, okay, what happens if alpha equals beta? Well, if these are both equal to each other, then we're going to get that they have the same trajectory. So there's an infinite number of intersection points that kind of correspond to all the locations here. We could also check things like what happens if alpha goes to pi over 2 or if beta goes to pi over 2. We can see that these tangents look like they might be pretty poorly behaved there, but they're in the denominator, so maybe it's not so bad. We'll end up with some x equals zeros, and that's kind of what you expect if you were to fire this directly vertically. All right, so there it is. There's our location horizontally, at least, where these two jets will cross. And if we really wanted to, we could take this and plug it back in for the x's in this equation and calculate the vertical location of that cross. Maybe I'll leave that as a little exercise to the viewers. At any rate, there we have it. Horizontal location of the crossing jets. QED.